wants to no one wants to dig up the road.
Right, of course. No, especially near its stately home. Here's
Yeah.
Clive.
Hi.
Hello, Clive. Well, he's put his headphones on.
Hi.
That's what I say.
Hello,
Yeah.
Alan.
Hi.
Good to see you.
Good to see you too. Yeah.
Gosh, I've so many questions that I was going to ask you. I can't remember them now.
Well, there's plenty of time.
Plenty of time.
Did
I'm sure you'll jog
did
my
you
memory.
did you
I
did you
can,
you've
sorry, I
did,
can
did,
turn off my sound if you want to discuss stuff in private.
No, David. No. It's nothing like that. Not for me, anyway.
Okay.
no.
I mean, Alan, I've asked you a question once when you spoke at the October thing in
Yeah.
HPAC. Other than that, it's only been a few emails.
Yeah.
I mean, I appreciate you must be incredibly busy.
Yeah. Yeah, well, I'm not that. I'm just slow at doing things now. I find
Oh,
I
is that
used
what
to
it
be
is?
able to. I used to find I could do all sorts of things so much more quickly now than I can now. So no, we've got some equipment for as a Royal Horticultural Society, and their weather station has died. So I'm taking that up to Leeds to get fixed. So I live nearby. So lots of little things just take over.
Yeah, I can well imagine.
Yeah.
Yeah, when you're dealing with real equipment as well.
Oh yeah, that's right. Yeah.
Yeah. Yeah. So I mean, and I pulled your as you saw your slides that you've kindly sent from October. I thought there was gold in there.
Yeah. Well, Stephen Salter had a lot more gold than I had, but some of them are his. Yeah.
Okay. Yeah. And we're all kind of scratching our heads and planning what can be done to get this to happen. When there's opposition and people that don't understand the need, really. So your slides in there about humidity and how it only takes an extreme weather event of high humidity and high temperature, and people simply can't survive unless they've got aircon. You know, they just die. You know.
Well, it's worse than that because in high, I advise the nuclear authority here, and high temperatures and humidities mean that control rooms in nuclear reactors don't work. So when you get the temperatures up to 30 or 40 degrees, and this is what a big problem with not just French nuclear power stations, but they've got quite a lot of them, and they have to switch them off. So when it gets hot, you're probably finding the electricity supply is under further pressure because there isn't the generation capability.
Because they can't cool their water.
No, they can't. Well, yes, but the cooling of the water has certainly affected the Swedish ones. But it's a mixture of the water. That's why they're usually located near the sea and the rivers, but also due to the fact that the air temperatures in the control rooms, and all the control rooms get extremely hot.
Well, can't they put aircon if it's a control?
Well, that's right. Aircon is very expensive in reality. It's not it's building the infrastructure for it. So I think it was in 2018, the French turned off 5 of their reactors because they just couldn't keep the temperatures down cool enough. And it's not just the control rooms. It's also the turbine halls, all sorts of other facilities, which makes it very difficult to keep the place cool.
Right.
So yes, the generation of electricity is going to become an issue. And Britain, for example, thought it was great. Britain thought it was great having lots of wind farms, and Scotland's got lots of them as well, but not. And you suddenly find in a high pressure, the wind isn't actually doing very much. So, so there's other issues there. And then if you look at some of the Mediterranean countries, they don't go down the solar panel route because the panels get covered with sticky sand and they have to be cleaned manually. So in high temperatures and humidities, there's the generation of power does become an issue. That so yeah, aircon is a problem, but there's going to be a lot of places that are not able to cope with these high temperatures soon.
I don't see that. I don't see that talked about much.
No.
And so that's kind of useful to put that in with a big long list of reasons why things like MCB are needed. I think it's time that I passed over to Robert, because he invited you originally, Alan, and I think we're going to have quite a lot of people here today. So I'll let him take over at this point. Robert?
Righto, thank you very much, Clive. And thank you, Alan. And we've got a couple of minutes before our kickoff time at the top of the hour for all of the different blocks all around the world. So welcome everybody to join us today. I think what I'll do is just wait for another 2 minutes while people join the meeting before introducing Alan. So if there's any other comments that people have just before we kick off, then let's just leave it at that.
Well, we usually have, I don't know, about 6 people arrive on time. Usually we're up to 15 today. So
I think what my preference is that we kick off on the dot of the hour, because it's often the case that we get to the end of the session and we find that we've got people who's still wanting to speak, and so I'd rather that people miss my introductory remarks than not have the chance to comment at the end. So
I think we have some new people. They could perhaps introduce themselves.
Well, I'm if people particularly want to, I'm not so keen on that. I must confess, Sev. But I'll give people a chance. If anybody who's hasn't been at our meetings before would like to introduce themselves just briefly, then please feel free. Look, I think we'll just kick off here. I'd like to welcome Professor Alan Gadian of Leeds University. As Alan is the visiting professor of dynamic meteorology at the National Centre for Atmospheric Sciences, based at Leeds University in the United Kingdom. And Alan is one of the world experts on marine cloud brightening. So it's a great opportunity that we have today to hear Alan and interact with him about his expertise. So I've got to know Alan over the last couple of years through our mutual friendship with the now late Professor Stephen Salter of Edinburgh University, and Stephen's great work in developing the engineering around marine cloud brightening is something that he's done in partnership with Alan. And so without more ado, I'll hand over to Alan.
Thanks, Robbie. Do you want me to try and share the screen from here?
Yes, please.
See if it works. I can't actually share it from here.
Try again. I've just clicked it.
Just a second. Right. How's that going? Is that doing it?
Not yet. Oh, there we go. No, not yet. Click the green, green share screen.
Yeah, is that getting there? Is that sharing the screen?
No, it's not. Is there a problem, Alan?
Yeah.
The green button at the bottom, share screen. Just click that.
I've done that. Yeah.
And then it brings something up, and you got to say whether you want to share your screen or a window or something.
Yeah, I've done that already. Yeah.
Oh.
And it's no. Is that working?
No.
Well, look, Alan, I've got your slides, so I can share screen if you'd like.
Yeah, could you do it? Yeah, I've had this problem before. I don't know. I've got 2 Zooms. Right. Yeah, if you could do it, that'd be brilliant. Okay. Brilliant. Thanks.
Okay.
Right. So the first slide is basically saying what's new, quoi de neuf, it's a French way, and if you could, this is the first part. Rebecca's sent the copy of the first talk, so I'm going to spend now about 20 minutes talking about 20 to 25 minutes and leave plenty of time for questions. So the first 6 to 8 slides are sort of a recap of what's new, essentially, and many of you will have seen this. So if we look at the 3 panels here, this is the sea surface temperatures. So the black line is the current sea surface temperatures. The orange line is last year's sea surface temperatures. And I would argue that the large temperature anomalies that observed last year were caused, but largely caused by the IMO reduction in sulfur. There was also a few other components like the El Nino, but essentially the lower left, and I think people have seen that before, is what the current state is. If you look at the North Atlantic, and of course in the UK we get obsessed by the North Atlantic, but also it has a big impact on the hurricane development areas. And if you look at the upper right panel, you'll see this very warm temperature of +4 degrees, 5 degrees, which is totally anomalous. And you don't really see this sort of thing in the normal pattern of things. This really is anomalous. And then the bottom right-hand one, you've probably seen this, is basically a reflection of those temperature increases. And I don't want to give the numbers out, but you can see that there is a significant warming. Next slide, please. We're still recapping here for a few more slides. Right, so this is what I referred to. This was the carbon brief, the emissions of sulfur emissions from international shipping. And you can see they've been rising, and some people say they can recognize COVID in there. But there is a paper which I've given a link to that I'm not sure is published yet, but it's by Yuan and Rob Wood, and I've got a preprint copy there, that have given the figure of 0.12 watts per meter squared warming. Hansen, that's the big drop there, just right where the huge decrease. Hansen would claim it's higher, 0.5 watts per meter squared, and that is consistent with a lot of the physics, but to actually put a magnitude onto it at the moment is very difficult. Now, if you think of double carbon dioxide as 3.7 watts per meter squared, and that's a really rough estimate, and if you think of something called the ECS, the climate sensitivity, now there's a paper come out very recently saying the climate sensitivity, equilibrium climate sensitivity, is actually 8+ degrees Celsius, whereas previously it was 5 to 6. So the rule of thumb I use is that if you double the watts per meter squared, you get an approximate equilibrium climate sensitivity. So what is the equilibrium climate sensitivity? This is the value, if you like, the planet would go to if there was no hysteresis, if no drag. And that has been one of the big arguments about Charney's work in 1978, when he said the climate sensitivity is quite small. And now people are discussing that and saying the role of aerosols in reflecting solar radiation is the key. So really in that upper left-hand side, that plot is that there's a whole area of science that's actually been discussed about what that is. But that would give 0.12 watts per meter squared, would approximately give 0.24 degrees Celsius, which is what some people say is actually happened. Now, the question is what's going to happen next year, but we'll come on to that later. The lower plot there is the El Nino. Now, the El Nino, it produces globally weaker than average trade winds, more rain and clouds in the central tropic Pacific, drier conditions over Indonesia. These are the standard properties of this warming, this warm water that moves across the Pacific. So this provides confidence that the warm anomaly will diminish, and it is diminishing. And some people say by the end of April that it should be, we should be between those two dotted lines. So
not advancing.
The effect of the sea surface temperature anomalies remains to be seen. Can I have the next slide? Can you see the next slide?
I think we're still seeing the first. That's better.
Can you see this slide of the magnitude of the future summer northern hemisphere? Right. So here we've got that this is the magnitude of in the future summer northern hemisphere temperature values. What I'm saying is here is you can see what is. You can look at it and say what is going to happen by the time we write July, August. And this is the latest figures. You'll see the biggest impacts usually in the northern hemisphere, and so you will just have to wait and see. So that's the real key. And I've seen a comment from Ron there, but I'll refer to that later. The next slide, then. They're still on the basics, and this is what I showed before. So what we've got here is definition of what is important in the atmosphere. And this Schmidt paper has not been challenged, and it's a very good piece of work. So if you look at the water vapor, it's 50% clouds, 25%, approximately, CO2, 19%. So remember that the rule of thumb is that high clouds, thickening of high clouds actually increases greenhouse warming, and low cloud thickening, low clouds actually reflect solar radiation more. So that's the rule of thumb. And that is why there is so much discussion of cirrus thinning, the role of condensation trails, etc. But I don't want to discuss that because this talk is basically on marine cloud brightening. So the whole question I'm doing, and if you like, I've added a little bit at the bottom there. So what happens if we increase the atmospheric temperature by 2 degrees Celsius? And if you go right down to the bottom there, you can see that in fact, the water, if you just look at the saturated vapor pressure curve, it increases from 0.023 bar to 0.026 bar. And that's about 14%. And that is increasing the sea surface temperature from 20 to 22. I've chosen those arbitrarily. And this is consistent with the Clausius-Clapeyron equation, where for each degree Celsius, the vapor pressure rises by 7%. So my whole thesis now is that carbon dioxide is a dangerous warming gas, but there reaches a point with when you have a look at the feedback processes whereby the CO2 is not the thing that I worry most about. I do worry about CO2, doubling CO2. And as I mentioned earlier, if you looked at some of the earlier assessments, climate sensitivity, remember this is the equilibrium climate sensitivity, what it will reach, is somewhere between 2.5 and 4. And New Scientist not long ago had an article suggesting that this is now 5 to 8 degrees. And this is what the planet will equilibrate at eventually. So now I've put role of doubling CO2 is minor. It's not minor, but the water vapor becomes much more important. So this, I'm still doing the recap here. Next slide, please. So what have other people said? And Rees, for other reasons as well, said that mankind has a probability of extinction, but one of the major reasons was global warming. Lovelock has said it's within the next 30 years. In fact, I don't know where I got that from, but it should be 20 years. It's a typo. So his thesis was that by 2028, that the planet will be in serious trouble. Now, he was using rule of thumb's arguments, so it's 20 years. Rule of thumb, he was using radiative balance, and he had an ability to see a lot of things, and I'm not sure that he got everything right, but if you watch the James Bond movies, he was supposed to be the Q. He was models of the person. The Q was or one of them. Hansen has given 2023, argues that 2 degrees C will be exceeded by 2040 to 2050. And the current rate is 0.27 degrees per decade. Now, obviously, one's always worried about where one lives, and there's European Environment Agency, Lena Yamano, I think she comes from Croatia, and she says that you prepare for at least 3 degrees C. So Hansen's prediction looks outdated. In Europe, southern Europe, the temperatures were 3 degrees warmer than. So the average for temperature is 1.77. So this, as all this work suggests the planet's warm. And if you talk to paleontologists, they will tell you that in historical terms, the changes are very rapid. So that's basically my recap. And if we just move on now to a few more slides. So this is a recap as well. Okay, yes, Q could have been inspired by, but Lovelock did work for MI5, MI6. So this is the standard picture. You all see it, and we're looking at the increased reflectivity of marine cloud brightening clouds down there. Next slide, please. So this is the Toomey effect. In fact, the first paper he wrote was in 1970, and then Slingo, who was he was a radiation physicist, and his models are still his radiation theory, single column theory, is still used in a lot of numerical weather prediction models now. Latham followed 3 or 4 months later in Nature, and he suggested it could be mitigated. And Latham 2008, 2012. And in fact, all the papers that started this off were produced. And he suggested a spray size of 0.2 to 0.8 microns. A little bit controversial, but anyway, that's what we're going to work with at the moment. Next slide, please. So you've seen this slide before. These are Stephen's, if you haven't seen them, this is Stephen's classic experiment, that if you take a certain amount of water vapor or a certain amount of glass, and you change the diameter of the glass beads in the jar, then you can make them appear whiter. And remember, the actual change in albedo we're looking for from these clouds is just 1 bar of that. So it comes, and the Toomey effect. Well, stratocumulus clouds cover more than 30% of oceans. They have a high reflectance. Toomey, and there was a big project in November 2008 And that was a picture taken of these clouds. And to remind everyone, seawater and air, energy derived from the wind, well, it doesn't really matter, but it's relatively inexpensive. It can be shut down, and you can actually control. And those were Stephen Salter's. Those were Stephen Salter's, taken directly from Stephen Salter's. The fact that it's low energy doesn't worry me too much. The microphysics of it is that if you spray in these stable areas, then you have a big effect. If you spray under if you spray under any storms or tropical storms, subtropical storms, it has no effect at all. Next slide, please. So this is really, these are just some of the papers, major papers. But if you look at Ralph Toomey, he died not long ago. Then the second one down is Slingo, he died. John Latham's died, and now Stephen Salter's died. So all the people who proposed this are now, I'm afraid, no longer with us. And they all, in the end, were trying desperately to make people aware. So it's up to, I say it's up to us now. But the last one, I want you to look at, notice down at the bottom, there's Robert Wood, and I'm going to introduce his name. He was sort of semi-student of John Latham's, and I'm going to talk more about his work. But those are some publications. And obviously it's biased to the work I've done, but sorry about that. Next slide, please. So let's talk about other ideas which is associated with marine cloud brightening. So Danny Rosenfeld and the group, in one of the groups in Israel, he's written a lot of papers on the effects of aerosol. And he was always arguing that if you spray small enough aerosol into clear air, not necessarily under marine cloud brightening, but you can call it clear air brightening, then it'll work as well. And so Rosenfeld's done lots of work on aerosol contributions, but he says, look, spraying in other areas has advantages. Not as efficient, but it works. And Haywood, Jim Haywood, has produced a paper in 2023, which actually does some numbers and says, oh, Danny Rosenfeld was right. So if we looked at some of the calculations we did, which was a primitive, well, it was a full climate model. If you seeded everywhere, you could actually bring the polar ice down to Iceland. Now, one of the critical things that underlies it, and I'll put it under Danny Rosenfeld's bit, is that Alkeskar and Christiansen suggested 0.2 to 0.8 microns. And I think most people, including Rob Wood, say 0.8 microns is the maximum. 0.2, some people like Rob Wood, and I'll come on to this in a minute, said you can use smaller ones, but essentially we're looking at the size range of the spray. So we're now going into some details, and Danny, if you talk to Danny, he would say yes, yes. He's also concerned about small sizes, but in the ANU presentation he made, he stated that. So this essentially is the abstract from below in below in one of the recent papers he's written, that there is a problem with actually the spray size. If you make it too big, then you're going to increase the rainfall and you change the droplet effective radius. So if you look down there. Now, this term effective radius comes in. So if you like, it's the sum of r cubed over r squared. So if you take those averages and you say, why is that important? Well, if you look at radiative calculations, that is the number that becomes most important. So fine, fine aerosols, the bottom sentences, could the fact is, if you made them too big, then you could increase the rainfall flux. If you made them small enough with fixed water vapor, then you could actually improve and change the effective radius in the way you want. So this is I've included in Danny, but this is one of the questions that I think we're okay with 0.2 to 0.8, no bigger than 0.8. So we're looking at some of the details now, and this is some of the latest work that's been done by Danny in late 2023. But he's just adding a note of caution, and we have to be aware of this, that you must make this spray reasonably small and not to spread to the large ones, because that does provide a problem. Next slide, please. So now we'll come to Rob Wood. So Rob Wood, I was his internal examiner when he did his PhD. And if you like, this group has made the most significant progress. So some of you might have seen this. He led the Vocals project. So that was 5 countries, aircraft scientists, and he looked at stratocumulus clouds. He wrote a review paper on it, an excellent review paper, and he's written many papers on stratocumulus clouds. At the time, John Latham and I tried to suggest we had some seeding experiments, but Rob, I think quite rightly, said we've got enough trouble measuring these stratocumulus clouds, just we're going to stick to this. So in April 2024, he produced a salt spray. Now, people can argue whether this wasn't seawater, but it was to show that, and there's an article in the New York Times, which I've included, which is dated the 2nd of April. So, yeah, there's some of the things I disagree with it, but we're talking about what's new here. Graham Feingold at NOAA, that's based in Boulder, Colorado, has also worked on stratocumulus clouds, and he has done some excellent work. And when I was talking with the ARIA project, I was saying these are the people you've got to include. His paper would suggest that you can use small. He had a simple heuristic model, so it isn't a dynamical model. He suggested that you can have lower than 0.2, and that might well be the case. But Daniel Harrison, well, he's doing some experiments on the East Coast, but no results. And there's other scientists, Grabowski, Marlowski, are also. So I've not included all the people there, but there is some work. But again, as was implied earlier, there is huge political lethargy. The solar physics, the solar stratospheric injection has had more support. Next slide, please. So what we've got here is, I'm getting some feedback somewhere. So Salter, he's producing experimental hardware, and this is being worked at in Edinburgh. And Newcommons actually produced a small spray, quite heavily dependent on energy, and there's still an outstanding question of how much energy it uses, but I still haven't been able to figure that out. So Armand Newcommons worked with Wood and Rash. Now, Rash was head of climate at NCAR, which is significant, right? Still getting some feedback. Anyway, Stephen Salter produced a disc, and I've seen it, and so I've seen Armand's, and he set up the Lothian School of Technology, and just as I referred to, Ali Price and Wyn Mampin are going to, and you can find further details on readbrighton.org. There's also group Sean Fitzgerald, Hugh Hunt, David King in Cambridge, and they're looking at different technologies. There's other scientists like John Macdonald, John, if I got this wrong. You've got this novel boiling water approach. But all these hardware opportunities need funding, and it's really quite difficult to get funding at this time. Next slide, please. So what I've tried to do, I've tried to augment what I published, what was published. I've not included it all. There's lots of other papers who've been done on marine cloud brightening. I've tried to give some of the latest observations. I've provided some more information, so look at it with that other article. The marine cloud brightening, I think, has been sort of, it's awful to say this, but the green lobby's IMO reduction of bunker sulfate production in bunker fuel has actually provided the first genuine experiment on marine cloud brightening, except it wasn't marine cloud brightening, it was marine cloud dimming. And that is why I'm now very confident, even more confident it would work. I've mentioned the groups that are working, but there are others. The hardware challenges are really significant. I mean, I can argue about 0.2 as a lower end or 0.05 microns, but the hardware challenges of producing the spray, and I've included some of the papers. There are many more. If you look at the end of this talk, there are more slides on the work I did. But the real point I want to make is that marine cloud brightening can offer an opportunity. And even David King now says that we've got to take this opportunity and do it. The problem with me and the other scientists, and even Stephen, was that we were actually useless at getting money and over political hurdles. And that's where I see the groups like Re-Brighton and HPAC actually being able to do it. We're going to have to do something. I think we've got to do the research. And in fact, there are other alternatives. I've not mentioned anything about SAI really. I'm always cautious about it because of the effects at the poles. But I think we've got to look at all the groups. The big advantage of marine cloud brightening is you can switch it off very rapidly. If there's any problem, you can switch it off, and within days, the effects will be zero. I'm going to stop there because that's my half an hour that I said. But there's some other slides on there from the previous talk I gave, talking about rainfall, talking about coral reefs. Okay, so I'll stop there, and there'll be lots of people probably wanted to argue, but let's have a go.
Thank you so much, Alan. A very good introduction to the conversation, and I'd just like to say if anybody does wish to comment, please use the raise hand function under reactions at the bottom. And if you're not speaking, I should have mentioned earlier, please put yourself on mute. We do seem to be getting some feedback from somewhere or other. We'll try and mute those who are not speaking. Let's see. We'll go first to Ron Baiman.
Oh, thank you, Robert. I think Brian actually had his hand up first, but that's okay. I did want to ask Alan about that number, the 0.5 watts per meter squared that you cited as Hansen's figure, and I mean I distinctly recall 1.05 for the IMO effect. I just wanted you to clarify that. I'm sure you have a clarification. I would also like to let folks know that we have a letter out to the IMO to do something about the bunker fuel regulations, warming reverse termination shock. No, it's actually just termination shock. It's just, but anyway, and I actually had a little discussion with Alan just a little bit earlier, and Well, anyway, I'll let Alan talk about that if he wishes to. But just there are a bunch of co-authors and folks who have signed the paper here, and so I just want to let you know that we're contemplating some further action on that. Thank you. Oh, and also, just sorry, one more point on the. Anyway, other people will talk about this, but in our response to our cooling document, we did have to try and clarify the role of MCB in the greater scheme of things with regard to coordination and governance and all and those other aspects. That it would be very interesting to hear your thoughts about that as well. Thank you.
Ron, can I just comment on that? It's interesting that the figure you gave of 1.05, 1 point what, which is it's very difficult. I found it difficult to get out of the paper whether he was talking about the 0.5 for the globally or the 1 watts over the ocean. So I've gone for the saying it's 0.5, right? Because it wasn't clear to me what is the global impact. Now, if you look at Rob Wood paper, it's 0.12 watts per meter squared globally. So you may be right. It may be referring to 1.05, in which case that is quite a big number. But it could. So I've gone on the lower figure just to say. I don't think there was anything else you asked on that specifically. But
coordination and governance, yeah, I did. I think it actually is 1.05 for the bunker fuel thing. I looked at that again, but I would appreciate your going over that.
Yeah, I'll have a look at it.
Yeah,
I'll have a look at it again. But I thought I'd halved it because I said it was only over the ocean areas. Sure. But that was I was being on the safe side.
Thanks, Ron. Brian?
Yes, I will note with interest the April 2024 paper on the low altitude volcanoes, for example, off Hawaii, that produce a steady stream of natural sulfate aerosols. And their results were very interesting because they indicated that cloud fraction actually dominated over the Tuomi effect in terms of rebrightening the sea downwind from the Hawaii volcanoes. And this effect was really substantial. And they noted a very strong gain, a very strong increase in clouds under humid conditions. And oddly, under less humid conditions, little effect or even a negative effect. So I think we should be paying good attention to cloud fraction as a key parameter as we consider these submicron aerosols going forward, in addition to the Tuomi effect. Thank you.
I agree totally, Brian. But yeah, I agree with you. The cloud fraction is an important point, and this also relates to when you heat up the oceans, the subtropical people like Mike McCracken sometimes says, oh well, it's 14%. But you heat up the subtropics and you get more clouds, so you're increasing the effect. So I'm being cautious again, but I think it's very, very valid point, and it does need investigating.
Yeah, I've actually seen some research from Caltech indicating that when you heat up the oceans in general, you get less of the low altitude marine clouds because of the higher saturation vapor pressure. That result is probably coming from, well, I'll remember Tapio Schneider, I believe, his research at Caltech is indicating that.
Yeah, it's complicated. Yeah.
Thanks, Brian. I should just mention that our meeting today was originally hosted by the HPAC, the Healthy Planet Action Coalition. Unfortunately, we weren't able to meet at the time that was originally announced 2 weeks ago, and so Clive Ellsworth and the NOAC group kindly stepped in, but Clive is recording the discussion, and we expect to put it up onto the HPAC website as part of the HPAC discussion series. John Macdonald.
Yeah, thanks again, Brian and Alan. Just further to your point, Brian. It's a parallel question to MCB, but Alan, I know it's a very active area of research, but in a warming world, do you think that cloud cover will increase with additional evaporation and more active agitation of waves and so forth, or do you think there will be a decrease in cloud cover due to less aerosols and DMS and so forth? But if it's less, then we obviously need MCB even quicker, don't we?
Yeah, there is a problem here, John, that the climate models and people who look at it, I can look at it from an analytical point of view, and it looks to me as though there will be no clouds, but people will say, well, you've got to run it in a model. So you've got to get a 1 kilometer model. And that is what some people in the world, in the US, Germany, UK, other places, Australia, are saying, you only know the answer to that question when you've got a 1 kilometer resolution model. The only problem is you're going to have a huge supercomputer. You can only do it once. And I think personally, from meteorology, I look at the old tephigrams and the thermodynamic diagrams, SCU-T, log-P diagrams. And if you do increase the surface temperatures, you do put more water vapor into the atmosphere, and this water vapor has to go somewhere, and it will condense. People have talked about this with hurricanes. Can you get higher than Category 5 hurricanes? And there is good argument to say you can't get higher than Category 5 because all you'll do is lift the troposphere up a bit more and the energy will dissipate. But when you're putting it into the lower atmosphere, there is a good logical argument to say that you are pumping more water vapor into the atmosphere, and therefore you should get more cloud out of the atmosphere because it will condense. However, you could say that in global warming, my results and other people's results have shown that when you warm the planet, you get longer dry spells and shorter wet spells, but you get more clouds, more intense rainfall. You've got to get the rainfall out. So I think you're asking a very difficult question, and I don't think there's anybody who could give you an answer, but my rule of thumb would be to say, the old meteorologist would say, you're going to get more cloud in mid-latitudes and probably deeper subtropical storms.
Mm. And if there's more rain, it may not be where you really want it either, where there's less water. So it may be over the oceans, but then it's going to be patchy. Yep. Yeah,
but the models do show. But the problem with the models is they're all based on parameterizations for rainfall, and the parameterizations have been tuned for now. So it's like the AI. The AI might be able to beat your weather forecast for 4 or 5 days, but you change the sea surface temperatures by a significant factor, which is what's happened now. Newfoundland's up by 5. What is the AI going to refer to? It's got nothing there to refer to. And you're going to have to solve the equations. So this is a big debate going on. What you need to understand the physics.
And as a quick response to that, John, I'll note the North Pacific as one example, and you just go up around the Bay of Alaska or the Gulf of Alaska, and you very commonly have the stratocumulus clouds for many months of the year. In contrast, the North Pacific just over Hawaii has these little popcorn clouds that, go up and down. And of course, it's much warmer there, but the cloud fraction is much lower as well. So after 3,000 hours of flying, I keep noting the contrast that at higher temperatures, you're getting these little popcorn clouds in the marine cloud boundary layer. And in contrast to a heavy stratocumulus base with a very high cloud fraction in the cooler ocean temperatures.
Thank you, Brian. Let's go on to Mike McCracken.
Thanks, Alan. Let me make
two comments in response to previous questions, and then I want to ask mine. The first is sort of, there is a 1 kilometer model. Mike Weiner at Berkeley Lab has one. He's run it. So, I mean, it is possible to run that kind of thing if you want. Second, on the issue of more water vapor leads to more clouds, that's just not really correct. The amount of cloudiness depends on the relative humidity, not the absolute humidity. And so if you, I mean, otherwise you wouldn't have any clouds at high latitudes and it'd be completely cloudy at low latitude. So it really depends on the relative humidity, and that depends on the circulation. So be careful of assumptions. So my question is, let's say you can brighten clouds. Okay, so I don't want to get into the physics of that. What does that do to the energy balance? Well, you're over the ocean. So what brighter clouds would do is reduce the amount of solar radiation reaching and being absorbed at the surface. That's very nice and everything, but given the ocean heat capacity, it's not going to really change the temperature very much at any one time. I mean, it's going to take a long time to change the temperature because of the heat capacity. And so, okay, that's nice, but how does that affect the weather? It's going to be a small temperature change. Is it going to do much? Now, on land, which is where I'd really like to have the cooling occurring or something, I'm all for long-term trying to get less heat into the ocean, but let's talk about land temperatures. On land in the summer, the dominant energy effect is how much solar radiation comes in. You're going to still have the CO2. So the marine brightening isn't going to really do anything in the near term to summer temperatures, warm season temperatures over land. In the winter, the dominant heat source for land, at least in mid and high latitudes and stuff, is the ocean. And so you would be cooling the ocean, but just a little bit. So it's going to take a while to really have an effect of getting the ocean really cold this way. And so I guess I like what they're doing in Australia for the coral reefs, because what they're doing is actually trying to cool the water right there where the reefs are or something. They're not trying to affect the weather at some distant point or anything. But I guess I'm a little bit, I think some of the assertions that have been made about what can happen to the temperatures in various places as a result of marine cloud brightening seem to me a little off. And I'd be interested in your comment.
Right. I think you're right in many of the things you've said. But one of the intriguing factors is that I talk about the meridional heat transfer. And that was largely, this was a surprise when we did the climate models. It really affected the meridional heat flux from the equator to the middle by large-scale systems. And this, you could actually see it in the intensity of not subtropical, the mid-latitude storms. So what you were actually doing was you were reducing the boundary layer temperature gradient, the boundary layer temperatures in the subtropics. And the question, Stephen Salt always said, we can do it at higher latitudes. And I think the result that we found was that it greatly reduced the meridional heat flux. Now, this has gone back to many papers that were produced in the 60s and the 70s and the 80s about the meridional heat flux, because in those days it was an active topic of consideration. So people like Slingo, Charney, all the groups on the East Coast did like, and looking at the numerical model results, and okay, the model had a resolution of 120 kilometers and it isn't realistic, but you are actually, why should this have an effect? You were hardly reducing the sea surface temperatures by a significant amount. But what you were doing, the model suggested, was reducing. So if you look at some of the model results, all you're doing is affecting this skin temperature. but you're also affecting the marine boundary layer. And this is what affected what we call the hurricane developments. So I agree with you. It was this curve that was in the 50s and 60s, and the students, we all had to learn how much radiation went out at the pole and how much was at the equator. And this is what was actually driving the meridional. And I personally think that this is why it has such an effect on the Arctic ice fields and the Antarctic ice field, is because you are actually affecting this meridional heat flux in a large scale. Green, Charney, Eadie, Schneider, all these people talked about the meridional heat flux. And I think that's what you're actually doing by concentrating the reduction in solar radiation reaching the lower boundary layer and the skin temperature of the sea, not the deep temperatures, but what Krauss and Turner would call his thermocline. I think that is the way I would try and explain it to you. And it appeared in the numerical models. Whether it's right or not, but it does seem to be a factor to me.
Was that a calculation that went some length of time, or was it a very short-term calculation?
Well, no, it was a long. So when we did ask, I would like some people to do it properly with a higher, but basically we ramped up the CO2 until for about 40 years, and then we let it settle for another 40 years. And we found that the sea surface temperature reduced, not greatly, but it was reduced to what we observed if we ran the climate model with no CO2 warming. And the sea surface temperatures were approximately the same, and it affected the meridional heat flux. And that is what I think I did when we did in the early teens, was the most encouraged and explained to me. And I'm afraid with Stephen, I could never convince him that the atmosphere was basically a heat engine taking heat from the equator to the pole, and it didn't matter whether you did it wherever you did it. That's what you were trying to reduce. Yeah, whether it's right or not, I don't know. But that's what the model was doing.
And two additional points, Mike, that I think worth bringing up. First is that for much of the ocean, the mixed layer charges its heat in one season. So in other words, from a winter to a summer, you're actually charging up with solar radiation the temperature of the top 20 meters to 100 meters of the sea, which have a profound effect on storms and also a profound effect on evaporation. Now, what's significant there is that if you just have one season of marine cloud brightening locally or regionally, you will actually affect the temperature of the top 20 meters of the sea profoundly as you're moving into summer and autumn. So this effect is really large. And then furthermore, when you do have regional marine cloud rebrightening, what happens in places like California is you have onshore flow throughout the late spring and summer that actually moves more than 100 kilometers onto land. And you have 10 million people in the Bay Area and over 20 million people in Southern California who are profoundly affected. And we see temperature differences of 15 to 20 degrees Celsius every time you have an overcast layer. The extent, duration, and magnitude, brightness, of course, of these marine clouds have a profound effect on tens of millions of people who are living near the coast, especially with prevailing onshore winds or summertime conditions where you have those conditions of onshore flow associated with a thermal engine of the summertime.
I lived in Livermore for 30 years, so I know what happens, and it's the heat on land that's pulling that air inward or allowing it to occur. And of course, yeah, under those coastal clouds, it does it. But I mean, I agree. You're trying to change the temperature of the mixed layer or something like that over time. The real question is how much energy and how rapidly you're really changing that and stuff. And I mean, I guess I want to see some high detailed modeling to try and see how that all works out. I mean, there's an awful lot of different processes going on, and you have to be awfully careful what you sort of say. But we sometimes got clouds all the way into Livermore, but boy, they burned off pretty quickly once the sun came out. So,
Well, let's see if we
Thanks
can
very much,
increase that
Michael.
extended
Right.
duration a little bit.
We'll
Can
go
I
on
just
to
answer?
Clive.
Can I just answer Mike once
please.
more? What really worries me, Mike, is what is happening over Central Asia and large land masses. And we've all seen the Haboob storms in Africa. And we're going to, I think, if the marine cloud brightening is not going to do anything to affect those huge dust storms that are going to be generated. So you're going to get a huge effect on mankind, even if you do manage to reduce the poleward heat flux, because the solar radiation is going to generate large-scale continental types of heating. So yes, I agree with you.
I mean, cooling the ocean over time is a very positive thing to do. I'm not disagreeing with it. I'm just saying that the effect on land is going to be a little indirect. You have to cool the oceans down to then get a real effect on land. And that's going to take a bit of time. Thanks.
Thank you, Mike. Clive?
Yeah, I wanted to ask, the only marine cloud brightening that I can see that's actually worked is the accidental, until recently, shipping pollution and volcanics. To what extent do you think, I mean, sulfur dioxide makes particles hygroscopic, they absorb water more easily, which means they can get across. Stephen taught us all about this Kohler barrier, that the Kohler curve, that particles have trouble. If they're too small, they can't nucleate a droplet, but if they're more hygroscopic, they're more easy. To what extent do you think hygroscopicity is important, Alan? Or am I wrong? Have there been some successful? Has Danny Rosenfeld been successful? In his recent.
Danny Rosenfeld focused on lots of clear air aerosol type activities. The results from the Australia Harrison are still not there. It's really the microphysics of cloud condensation nuclei is incredibly complex, and you're not going to get an opinion from most cloud physics like Grabowski or Feingold on that. You might have got an opinion from some people like Prufacker, but he understood it. But it's a very complex microphysical process, converting sulfur. You had people studying DMS, which I know Brian's interested in, as a production of aerosols. You have people talking now about the dust from mining activities. Can that happen? So I'm going to avoid the question completely, I'm afraid, because I really am not confident in answering that. But just before I leave it, I know it's a side issue. I mentioned this to someone high up in the EU Commission, and they're petrified not with the global warming, but what happens if the AMOC collapses. And the AMOC collapse is seen to be associated with the melting of the ice in Arctic. So there's lots of other implications, because if Europe dropped its temperature by 5 degrees, it would have a huge, profound effect on agriculture. So it's not, marine cloud brightening has other consequences, that if you can protect the AMOC and things like that, then the planet has a better chance of not tipping over into some new state. But anyway, that doesn't answer your question.
I thought I'd try anyway. Thanks, Alan.
Thanks, Clive. I just wanted to shout out to a couple of our guests. We have several people from the Lothian School of Technology, Ali Price, Wyn Rampen, and Jamie Taylor. Very good to see you along today, and Olivia. And also Armand Neukemans. Armand, we in the marine cloud brightening community, you're one of the luminaries, and so it's wonderful to see you along today. I'll hand over to Franz.
So I wanted to mention the chemical aspects of clouds, because meanwhile it has been found out that small droplets, which condensing droplets, produce H2O2, and this H2O2 produces OH radicals when lit by sunshine, and this would be a depletion effect for methane. So if we brighten clouds, this effect is much more essential in small droplets of lower than 1 micrometer, and this H2O2 concentrations also increase in small droplets. So the upper side of clouds, which is lit by sunshine, acts then as methane depletion chemical. So this kind of cooling should be mentioned also, I think. And these effects of small droplets is studied in the Stanford lab by Richard Zari. I hope I spoke it right.
There, I think they say.
Also in other labs in France and other places. It's a rather young science. That's it. That's all.
Alan, any response?
No, thanks for that. Very interesting. We did a lot of work on H2O2 and ozone, but that we hadn't even thought about that in any success. But that's interesting. Thank you.
Thank you, Franz. I'd like to comment to say that the politics of marine cloud brightening is incredibly contested. I was pleased to see an article editorial yesterday in the Washington Post calling for consideration of solar radiation management and solar geoengineering, but couched in very equivocal terms, just saying it might be needed, and just a whole lot of qualifiers around the concept. And then I always find it fascinating to look at the comments that the readers make, and the most popular comments are just uniformly hostile. It's viewed as something that's not needed, as a distraction from the priority of emission reduction. And so just the general community has a bit of what I see as a sort of fantasy mentality, just unaware of the security danger that's created by some of the information that Alan has shared with us today about the extremely rapid temperature rise. And so there's this urgent need to get the advocacy perspective out into the mass media, where like even we're seeing some openness with this Washington Post editorial, but that's a fairly unique thing, and it's still not advocating rapid investment and development. We have this problem that's generating submicron spray is a engineering problem that has not yet been solved, and we hope that that various groups such as Cambridge and the Lothian School and others will be able to solve it. But it really needs a much stronger public focus. It's very welcome that the Advanced Research and Invention Agency, ARIA, in the United Kingdom, has proposed a significant investment, and it's if people on this call wish to find out more about that, then our group at Brighton is supporting the Lothian School in its work to develop proposals for funding from the UK government. I see that as a very significant opportunity, and it will need quite intensive effort to get that support and to get the implementation of marine cloud brightening. I think that the safety issues are really a big furphy, that is a distraction. Marine cloud brightening is just far safer than the alternative of not marine cloud brightening. So I just wanted to throw in a few of those comments, Alan, around the political advocacy dimension and the need for investment to move this work forward.
Yeah, I agree with you, Robin. And Armand, I mean, he did the spray and then he got no more funding for 10 years. And it is a huge political problem. And the fact that we've had this huge green experiment, which has produced marine cloud dimming, essentially, has encouraged me. But I don't know how I just think there has to be another, hate to say it, Hurricane Sandy or something catastrophe like that for people to actually to wake up. But Armand got some money years ago, and I don't know whether he's got any more since, but it is a huge people like Bill Gates were terrified of the political opposition for funding this sort of research. And that's where Stephen Salter, John Latham, but we're just useless because we could never overcome that funding. It's really an appreciation of the necessity to do something. And even if someone like David King or Lovelock says it, completely ignored, we've had no hope. And even Paul Crutzen at Armand's house years ago said he preferred marine cloud brightening because it's better than his sulfur injection idea, which shocked me a little bit. But I've seen the email. We're going back 20 years, and I've made no progress, and others haven't. Politically, we're naive. I don't know how we get around it. That's why I hope organisations like yours and HPAC can actually do something.
So
it's really important that, for example, James Hansen in his Global Warming in the Pipeline article commented that marine cloud brightening, as proposed by Stephen Salter, is the most innocuous way to begin to address solar radiation management. And I think it raises the importance of marine cloud brightening in the sequencing, that it may well be that the world will come to a view that stratospheric aerosol injection is needed, but we're a very long way away from that sort of view. And what's needed is efforts to test the more innocuous and acceptable forms of sunlight reflection, and this is where marine cloud brightening is most important. We'll move on to Jonathan Cole.
Thanks. Yes, Alan, you spoke about how we need to push the climate community towards, the recognition that spending the $1 trillion a year on CO2 drawdown is spending a lot of money on one thing, but almost nothing on the reflective, efforts to work on the forcings. So I want to show you a slide and see if you think we're ready to use this kind of a slide to start to push them away or push them towards recognizing that the global dimming is actually currently this year and maybe in the years upcoming, it's going to be the major cause of rapid heating, and it won't be so tied to the yearly CO2 emissions.
I mean, I agree that global dimming is. I used to say this about Australia. When you actually looked at the huge clouds of dust over Australia and the dimming that was caused by the basically open quarrying type, it's never appeared in any of the calculations. We did it when we looked at the vocals experiment, but because the smelters off the coat, the copper smelters weren't producing their pollution. But I don't know, but or astronauts have always talked about global dimming in this, and it's a factor that doesn't come in any numerical model. Although, if you look at the work of people like Bjorn Stevens, he does talk about it. So, yeah, it's all the same process that we're talking about here. I think we've got to the stage now where we have to reduce the solar radiation coming in somehow because of the water vapor feedback and other feedbacks. But I can't comment on that.
That's a very clear slide. So thank you for sharing that. So Jonathan, if you can unshare, stop sharing the screen, and we'll jump straight to Armand, if that's all right with the others. Armand, please.
Yes. So thank you. Let me first say something in defense of Bill Gates, right? So we were actually attacked after the Asilomar conference, all right? So a guy called me from the London Times, and he says, well, I heard from Stephen Salt, or that's how he got my phone number, that Bill Gates has made got this group of rogue scientists essentially in California that's going to do the work for him. He's going to decide that, and so anyway. So actually Bill stood up for us and defended his position and all that kind of stuff in a very reasonable way. The only problem is that basically his foundation didn't like that. And so he said, look, you get a lot of bad publicity from this couple $100,000 guys, $100,000 that you give, and we spend $20 billion a year on this essentially, and we get very, very good publicity. So anyway, that was sort of the end of the support. That he may come in at one time or the other. He has supported the experiment, essentially SAI and all that kind of stuff. So in defense, but it turns out that after working on 15 years on this, okay, this is a much more tough problem than we ever anticipated. Okay, so I've done the Rayleigh instability and all that kind of stuff for 5-6 times in my year, and when we took this problem, they said, oh, in 2 or 3 months we'll have a solution. Yeah, we had a small-scale solution, and in the lab we made beautiful crystals, essentially 80 nanometer diameter, just about all the same. Okay, perfect. All right. Well, scaling this up isn't actually a piece of cake, is what it turns out. And so the thing that you have to remember, the path that we have taken is that we published a lot of this essentially various methods. Some of it worked and didn't work. Okay, what we have taken essentially is effervescent spraying. All right, and that actually because it was the fastest way to get to something that could be easily implemented. Okay, and say, yeah, is the stuff going to lift or not? And that's what they demonstrated in Australia. Just for example, the particles that Steve Salter was making, 800, 900 nanometer in diameter droplets, okay? There's been a simulation of this, and you see them fall exactly to the ground floor. There's just too much evaporation. So we've actually worked on the other side all the time, where we think, yeah, this is still going to convert, okay? If you have a 0.5% relative humidity and all that kind of stuff. Because, what you have to consider, it's not only the best particle, okay, that from a physics viewpoint is best, is the generation efficiency. So if you look at some unpublished data from Australia, you get some conversion at 0.4, I'm sorry, at 40 nanometer, okay? And maybe at 80 nanometer, essentially, you get maybe double of that. But typically, you make 8 times more of the 40 nanometer because the diameter is quite smaller, so 8-fold increasement, okay, than of the 80 nanometer. So anyway, that's why, it's not clear. It's not necessarily the physics of the clock. It's your generation efficiency, and that's important. And so right now, and Brian knows about this and is probably better informed than I am, we're working on a system that in principle looks very, very interesting, okay? This was generated, I mean, communicated with by the Australians. There's no secret about this. This was work that was started in Delft University in the 1990s, okay? And the reason it was started actually is to increase the efficiency of gas turbines, okay? When you have a gas turbine on the first axis, the first one is you compress the gas. Well, it turns out that takes about two-thirds of the power that's on that axis, okay? So all the other stuff they get out is a small fraction of what you need to compress the air. So, you know, people have known this really for a long time. You had a very high about the compression. And so always then can we, you know, go to isothermal. And if you do this isothermal, in principle, you get a 25% increase in efficiency, which is phenomenal. And you also reduce the flame temperature, so the NOx emission and all that kind of stuff go down, all right? So these guys thought they had it slicked. Actually, they started commercial turbine development in the 1990s. Can go back to publication of 2001. It's called the double head thing, okay? So it looks very attractive. The droplets are 4 micron or something like that, the estimate. So if you take flashing hot water, okay, it actually somehow magically produces a relatively monodisturbed distribution. Very attractive. So then they started this commercially and turned out, that's the only thing I could find about it. I have connection in Delft. Anyway, they had to stop it because the big droplets didn't evaporate in time and they ruined the turbine blades, okay? So, outer first. So the Russians took this up in 2009. It's a very, very well-known institute in Moscow. It's not one of the backlands, okay? They worked on it for another 10 or 14 years now. And they've gotten down to droplets where 90% of the distribution, 90% of the mass of the distribution is in 140 nanometer droplets, which is very, very attractive. Okay? So that is very, very intriguing. And so this is what we're trying to explore now. And the beauty of this is that it only leaves us heat, okay? So you have to heat up the water from, you know, room temperature or whatever it is to about, say, 200 degrees C. That's where most of their experiments was. And there are a variety of parameters that you can change. So that'd be very, very attractive because in principle, as Brian knows better than I do, you could sort of, you get like 10 to the 16 drones with a 30 kilowatt that you could actually almost generate from solar power, okay? So that's what we're working on. Whether that's going to work or not is still a matter of dispute, but it's very, very attractive. And if you did have that really going, right? If you install that, you know, never mind the agreements that have to be made, but you could install that in the chimney of ships in very, very short time and be guaranteed that it's going to go up and all that kind of stuff. But apart from, of course, that as I realize more than ever before, that cloud science is extraordinarily complicated and we really don't know what's going to happen. So that's my input on all this after 15 years of work, and several other members of our team are here on the call. So Lee is there, and Suds is there, and Gary is there, and Karl is there. Anyway, so.
That's very interesting, Armand. Thank you. But 140 nanometers isn't much different from 0.2 microns. So
no, that's 140 nanometer droplets. It goes down by a factor of 4. And if you need a little bit larger, you can double the salt concentration by, and all that kind of stuff. And then if you really need to, you could spiral them around in a cyclone, and at very high concentrations of these kind of droplets, you actually get to coalesce them in very short order.
No, it looks as if it's in the right ballpark, definitely. And
so,
what worries me is producing 0.8 micron droplets, because they will actually, as Danny Rosenfeld said, they will start destroying the properties of the structure. So you've got to keep it small. But
so let me go back to this, if I may. So basically, that's what killed the turbine experiment. Okay, so you have this large scale that droplets itself are, sort of from the Russian articles, a little confusing and all that kind of stuff. They're going anywhere quite a bit over, 1 to 10 micron. Okay, so you want to eliminate that. But we think there are enough techniques that we've learned in NOAC that there is a good chance that you might be able to eliminate this. So for example, think that you hit this on a super hydrophobic surface, okay? So the problem with it is that superhydrostrophic surfaces they're not very strong right now, but you can see a dramatic increase. At least we've seen it on occasion. That is still not for general publication, but so there are other techniques. So the Russians now, according to the publication, and it's been going on for 10 years, right? It's very hard to understand, and so anyway, we're doing the experiment as good as we can. So you got 90% of the mass of the distribution, okay? 90% of the mass in that 140 nanometer distribution and 10% in the other. And that's what we'd like to find out. And in the experiment that we've done now, we're not seeing anything like this. But anyway, we may be doing the experiment wrong for the moment. So it sounds very simple, but then there are various things that come in that make it a lot more complicated than we thought. Mm-hmm.
Thank you very much, Armand. That's really interesting and good to hear from you. So we've got about 10 minutes left, and we've got 4 people who would like to speak. So we'll just go to each of them briefly. Firstly, Gregory.
Thank you. My question may be partially addressed by the previous speaker, but I've never had a sense of how high you want the spray to go for marine cloud brightening. What sort of general altitude you want it to get to? Maybe somebody could answer that question. The other comment I was going to make is that
I'll just say on that, my understanding from Stephen Salter was that if you generate a submicron spray at sea level, then it will form an aerosol layer above the ocean water, which will then be warmed by the sun and raise up into the boundary layer quite naturally. So that's how you get from the sea surface up to the cloud layer.
Let me ask you, there's a caveat to that, okay? Anything that you spray is charged, okay? It can be substantially charged. So when you spray even the water essentially like that, by whatever it is, okay, even if you just with effervescent spraying is charged. So you're going to have an image layer, an image layer of that cloud essentially in the ocean. And whether those droplets are going to survive or not, okay, is very much in dispute. So that's what I'd like to point out. When you're spraying from a concentrated source, okay, it's not like you're doing it from the ocean, okay? So from a concentrated source, you have concentrated evaporation, and the thing falls down to the ocean. That's what they've demonstrated 12 years ago in Karlsruhe. So that's why we always have tried to go to the other side. So whether that's right or wrong needs to be seen.
Yeah, Armand, if you do it at 30 meters, though, or 20 meters, and you've got the natural circulation in the boundary layer, you're going to lose a lot, I agree, but you only need a relatively small efficiency compared to the numbers that you produce to actually get in the clouds. So from the dynamical motion underneath stratocumular clouds, and that's where there's the big advantage, you get these large scale eddies and you're getting centimeters a second. So you're going to get some of these advected out of this near surface layer. So I'm not quite as pessimistic as you on that.
Okay, let's go on to Greg's second
yeah,
question.
I'm sorry. I was going to tag in, another question on top of that comment, which is that all this research that needs to be done, as far as I'm concerned, needs to be done in conjunction with actual experiments to really move forward. That's crucial, and that's true with SAI. Now, marine cloud brightening can be done more locally, but the relative harmlessness of doing initial experiments compared to the CO2 experiment of 40 gigatons a year is so profound that it's illogical not to proceed immediately with actual experiments, which are right now just banned above anything else. I mean, everything is banned except experiments which are so trivial that they can't possibly hurt anybody, and yet you can't get it's a total ban. And I think the way science works is comparison to experiment, and you can't go to the point of completing all your theoretical studies and say, we now know with 100% certainty, this is the answer, and now you can go forward. I mean, it's absurd. But anyway, that's just a political statement, obviously, but whatever.
Thanks very much, Greg. We've got 3 people wanting to speak, so we'll just jump to each of them. Herb, please.
Thank you, Robert. So I don't know how many people saw just in the last few days, in addition to the Washington Post editorial that Robert referred to, there was a paper by Wake Smith and colleagues, and he said, and I sent this around, I think this is one of the most significant quotes I've seen from a solar geoengineering researcher. He says, mitigation alone, and we say, emission reductions alone, is no longer sufficient to secure the future climate that we and our successors on this planet will desire. So taking that, I'm in Washington. If I am the advisor to the president or the secretary of NOAA or the head of NOAA, which happens to be actually right across the street from where I live, and I say, here's the Washington Post editorial, and here's the Wake Smith column. This is just this week. What should we do? And he says, well, I want you to bring in the leading researchers on MCB to brief me, and I want them to tell us, first of all, do they all agree on the nature of the kind of research that still needs to be done? How long will it take? What are the risks of the research? How much will it cost? And how certain will we be at the end, quote unquote, of that research that we'll be able to reach an answer where we can say, yes, let's do it either on a small scale, a large scale, or let's not do it. That's what I'm looking for as a policymaker or as an advisor to a policymaker. And in real life, I don't have direct access to people like that, but I know a number of people who are my neighbors and colleagues who do have access to people like that. So that's what I'm looking for.
Thank you, Herb. I think with the short amount of time that we have left, we'll just accept that as a comment. Alan, of course, you're also always welcome to respond. Otherwise, we'll go back to Franz.
I only wanted to say we think we have an idea to make these nanometric particles simply from the gas phase. For instance, if you use a gas phase of hydrogen chloride and plus ammonia gas phase, you get at once extremely small aerosol of ammonium chloride. That's an extreme simply thing.
Thank you, Franz.
That's it.
I think Clive provided some comments about that in the comments. So perhaps Clive.
Yeah, I was going to say the same thing. Be interesting to know what to hear what Armand has to say about that, making nanoparticles by mixing gases.
Well, I'm certainly not a chemist, and so anyway, my concern was, but actually the group where we're working for the moment is
so
very.
I'm on a panel discussion on marine cloud brightness.
Yeah. Go on, Armand.
Yeah, so we have never tried to make the things from gases itself. I mean, that's what happened in the stratosphere essentially. But we've always stayed exactly to thing. And if you want to spray them very finely, you could do very, very fine droplet spraying. One could conceivably think of putting the iron trichloride essentially in the thing and spraying at 170 degrees C, and it's going to survive it. Actually, the group that we're working with in our lab actually uses iron trichloride to basically clean up your drinking water. That's what they're doing right now.
Mm-hmm.
So,
yeah, thank you. Thanks, Armand.
There are many suggested ways of creating submicron spray, as well as a recent paper that's used an alcohol process with dry salt, proposing the release of dry salt nanoparticles from airplanes instead of from the surface. And so all of these different technologies will need to be examined and tested. One of the things that Danny Rosenfeld's commented was he visited the test that was conducted on the Great Barrier Reef in February by Daniel Harrison and Southern Cross University, and said that while they were able to generate submicron spray, they used such a large amount of electricity to do so that it was not economic. And so the question is the scalability and the ability to bring down the cost in order to make it effective. So let's see, we do have a couple of minutes, and Ron.
Oh, thank you, Robert. I just on your point, and I think you may be referring to the paper that Andrew Lockley was involved with.
Yes.
Yeah. So in that paper also, and I don't know, I may have not caught that in your remarks, but they propose a method, a distillation method, to create the small particles, which I would be curious if any of the MCB experts here have any knowledge of that or thoughts on that.
Well, if you want me to answer, this stuff that the effervescent spraying was put in place to put a method there that could get us there rapidly, okay? With the few resources that we had, all right, let's put something that can actually put in place, and you take a couple hundred nozzles and you spray with it. Now, we're not up to the nozzles were then improved and all that kind of stuff, but that was not necessarily to do the most economical thing or the one that you should use, okay? Because basically it requires a lot of energy, and the very best results that you have, about 10% of the mass, okay, goes into the spray that you want, and the rest is stuff that no bigger that you would like. That's sort of what we found, and so maybe SRI is doing better now, but that's the number that you have. So. But
yes,
the
so
stuff...
I think the main barrier remains the politics, because we saw with the COVID pandemic that when there's the political will, that it's possible to produce a vaccine at warp speed. And I think that we need that same sort of political recognition of the security problem of the temperature, the sudden temperature rise that we've seen, in order to provide the resources to find out what is the most practical way to do marine cloud brightening, and to start moving it forward, and to really address some of the misinformation that's so widespread now, that's preventing us from moving forward. Now we've reached the end of our time together, so I'll just provide just one last opportunity if anybody would like to make a final comment.
Can I just say that the political aspect is crucial, and the other aspect that's crucial is the fact that if you now say to people, and I wrote a paper for Nature and they rejected it, that CO2 is now not the major warming element. It's the feedback from water vapor. It's been completely rejected. And so it's not just the political aspect of interfering, is you've now got the reticence of scientists saying, we've got to get CO2 down. And it's as you were saying just now, Ron, the acceptance of, or Herb, can't remember, the acceptance that we're actually overheating and reduction of CO2 is now not the major concern, is a huge political barrier as well.
Well, that's just not correct, Alan.
I think it is.
CO2 acts as I just reviewed a paper about it. CO2 acts as a spigot that lets the water vapor feedback occur.
Yeah, I agree. I totally agree.
You don't have CO2 capturing in the upper troposphere, then all the heat will just go out. But by more CO2, it captures there, and so the heat.
Yeah, I agree with
cannot get out. It's sort of a controlling thing.
Yeah, I agree with you. CO2 was absolutely critical, but now we're getting to the stage where we're getting this feedback, which is is making matters worse.
Well, we've always had the feedback, but that's.
I know we have, but yeah, I agree. Yeah.
We're at a dangerous level.
The practicality, Alan, is that we actually can't do anything about CO2 at a scale and speed, whereas we could feasibly do something about water vapor by increasing albedo. And the best way to increase albedo in the short term appears to be marine cloud brightening. So I do hope that there will be a sea change of sentiment, and we'll be able to move forward.
The way you affect it is by reducing the solar. That's what you've got to do.
So I'd like to take the Alan thing, but my own thing, if you change the story now, okay, and that CO2 says is not important, okay, you lose every credibility that you have ever had, okay? You know, I have a hard enough time to convincing people that are really in favor of this, okay, that when we reduce this pollution, it's actually making it worse. You be very, very careful how you think that, and explain it a minute ago. The CO2 is the problem, okay, that's what we know. And there are other facts that we now understand, but if you change the story, you lost everybody. They're going to say, look, these cloud scientists don't know what they're talking about, period. That's the end of the story. That's easy for somebody to bring out on the radio, and that's it. You lost them all.
Well, that's exactly right, Armand. But the issue is that it's not possible to, like, partly because of committed warming from past emissions, and because of the political and economic drivers of ongoing emissions, that the prospect of actually doing anything about CO2, like it's expected that emissions will still be up at 50 gigatons a year in 20 years' time, and so there's a lot of hand-wringing, but it's really difficult to actually do anything about it. Whereas we could achieve a change of thinking if we introduced marine cloud brightening, is my assessment.
May I say also that what Armin is saying is effectively the scientists have to pull their punches and engage in managing their message, irrespective of what they know. That seems to be not unscientific, but political itself. Could you answer that?
Well, no. I mean, the CO2 acts as a spigot. It basically controls how much the water feedback can be. And so
I understand the general process.
And so solar helps make the process go. So you either have to reduce the solar or get rid of the CO2 to get the energy out of the, keep energy out of the system. You want the system to have less energy. So less solar.
Are you saying, Mike, that marine cloud brightening simply doesn't work? Is that what you're saying?
No, by reflecting more solar, if it can reduce the amount of solar, it's ultimately going to cool the ocean or something like that. And that reduces, a lot of the evaporation comes from the ocean, so it reduces the evaporation.
So you're just saying that the water vapor is a red herring.
Oh, well, no, water vapor is a feedback, and it creates the largest, it looks to be the largest flux effect, but it's controlled by the CO2 or the amount of energy coming in, the amount of solar energy that's absorbed, which drives the hydrologic cycle. So
and so that amount of energy
one or the other
is the albedo. So I'd like to hear from Jeff Haley.
Before we adjourn, can I ask each person who has details on hardware that can be used to make small salt droplets? I would like to study all of those hardware designs.
Thanks very much, Jeff, and be happy to follow up with you. Franz still has his hand up. Is that, do you want to speak, Franz?
I wanted only to say something. I would give ideas about the gas phase salt production. The other thing is to make CO2 depletion, transforming from air to sediments, is the simplest way is to plant trees, because plants they have the best method to to extract to make weathering, say, and they do it by their root system. And if you burn plants, you see how much ash is in them, and all this ash goes into the ocean as hydrogen carbonate. That's all what I said.
Thanks, Franz. Clive?
Yeah. It'd be wonderful if we can prove, which shouldn't cost very much at all, that methane, because methane, we know that methane's zooming up. If we can think about generalized CO2 to more to just greenhouse gases, methane has nearly tripled since pre-industrial times, and it's, as we know, a much more powerful greenhouse gas. If we can prove that it's removed by, or that that hydrogen peroxide is made in small cloud droplets when they evaporate, and which is bound to be removing methane, then we'll be able to say, well, okay, we can reduce the greenhouse gas problem quite a bit. Maybe I don't know if it's 20% or something, and marine cloud brightening would come along with that, be a bonus. So we'll cool the oceans at the same time. Maybe that wouldn't be the main objective. The main objective would be to remove greenhouse gases, which is what there is political capital for. And then maybe marine cloud brightening can come in as a bonus on top of that. That's my comment.
Thank you very much, everyone. We'll end the meeting at that point, and thank you very much for attending. Thanks especially to Alan for your presentation. Really appreciated, and to all of the excellent discussion. And we look forward to seeing the recording up on the HPAC website. So we'll end there. Thank you. Goodbye.
Thank you, Robert.
Ciao.
I'll send the recording soon.
Thank you.
Thanks, Ursula.
You're welcome, Ursula.
Thank you.
Bye-bye.